Okay, so per the previous examples, I have shown you all these cases right here. I've shown you the case of polynomial, exponential, and the last one is on sine and cosine. And now I'm going to show you the fourth case, so which is going to be on linear combination. As I mentioned to you before, linear combinations mean function are combined together with either being add up together, or like it's going to be, whether it's going to incorporate additional operation or subtraction operation. Okay. Alright, so I'm going to demonstrate by using this particular example. So I'm going to be solving this equation over here, d square y over dx square minus 3 dy dx plus 2y, and that is going to equal x square plus 1 minus exponential of x. So if you have a look over here, so I have two functions being combined together. So x square plus 1, they are together. So remember, when you have a constant is actually part of a polynomial. So that is why. So these two, they are going to be the polynomial, and this is going to be from the exponential. So basically what we had over here, so we have a linear combination that involves polynomial and exponential. Alright, so the idea how to solve this is still going to be the same. So first of all, I'm going to start by finding the YC. And for this case, I'm going to have m squared minus 3m plus 2 equals 0. This is going to be the case of, I think it's going to be distinct roots. So I'm going to have 2 and 1, so minus and also a minus. So for which I'm going to write that my YC of x, because my variable is x, is going to equal a exponential of x plus b exponential of 2x. So that is going to be my YC. So now that I already have my YC, I'm going to start delaying and find what is going to be my YP. And for this case, my function f of x is given by x squared plus 1 minus exponential of x. So now I'm going to consider them separately. Okay, for this case of polynomial right here, so my family of derivative, so that will be given by x squared, x, and also 1. Okay, remember, so 1 is also part of the polynomial. Whenever you have a constant, combine it together with the polynomial, they are together. Do not separate the constant and the polynomial function to the power of x to the power of 1 to the power of 2 and so on. Okay, and for this one, so for this exponential, so my family of derivative is going to only involve one element, which is going to be the exponential of x. So what we're going to do, so when we write the yp, so we are going to combine these two functions. So what happened is that my yp of x, so I'm going to start with the polynomial. So it's going to be cx squared plus dx plus e. So let me put a bracket around. So this is going to be for the polynomial plus, and for the case of exponential, so let's say I'm going to put that as f exponential of x. And let me put a bracket around for this one as well. Okay, however, so let me put a remark over here. So when you check for linear dependency, so check each bracket individually. So check each bracket individually. Okay, for Li or Ld. Okay, what do I mean by that? Right, so here when I check for linear dependency, for the case of YC, for when I drop a and b, my function is going to be exponential of x and exponential of 2x. And when I check with the polynomial, there should be no problem. So because my function is simply given by x squared, x, and also 1, none of them are what I call that the same, so they are going to be linearly independent. So I have no problem with YP. Okay, however, so that is going to be a problem with my YP for the exponential, because here what happened is that I have exponential of x, and at the top over here is also in the form of exponential of x. So both of them are equal, so they are basically linearly dependent. So what should I do? Like, one function is linearly independent, so the other one is linearly dependent. For the one that is linearly independent, so you simply retain that. So let me write it down here. So my yp of x, so this is already linearly independent, so I'm just going to copy it down so it retains. So I'm simply going to have cx squared plus dx plus e. But for the case of the exponential, they are linearly dependent. So what I have to do is going to be the same as what I have done previously. I'm going to multiply this by the independent variable, which is going to be x. So my new function is going to be fx exponential of x. And as usual, so whenever you have written down the new one, you always have to check whether they are Li or still LD. And for this case, when I check, so now they are going to be linearly independent. So both of them are linearly independent, then only I can proceed, and this is going to be my YP. Remember, when you write down the family of derivative for each of the function, you consider them individually. Okay, so if only the exponential is LD, so only the exponential is multiplied by x. And if only the polynomial is LD, only the polynomial is being multiplied by x. But the one that is already Li, leave it alone. Don't bother with it. Okay, so that is what we did over here. So now, as usual, so I'm going to have to figure out what is going to be the value of C, D, E, and F. And we're going to have to differentiate this twice. So my first derivative, so I'll end up with 2cx plus d plus 0, because when I differentiate e, that will be 0. And when I differentiate that, let me factorize the exponential of x. I'm going to apply the product rule. So I'll end up with f exponential of x plus fx exponential of x. Okay, you can try to figure out product rule, and you will get exactly the same answer as what I get over there. Okay, and then I'm going to differentiate that again for the second time, a second derivative. So y double prime of x. So I'll end up with 2c plus 0, because when I differentiate d, that will be a 0. And here I'm going to have exponential of x multiplied by f plus fx. And when I differentiate that again, so what happened here is that I'm going to assume this is going to be u and this is v. So I've shown you this in one of the previous example in exponential. I think it was the fourth example, so refer that for the product rule. So here I'm going to have f plus fx, and when I differentiate that, 0 and 0, so I'm going to end up with another f over here, so which actually 2c plus f plus, so it's going to be 2f because f plus f, so fx exponential of x. So that is how my y double prime looks like. And now we're going to substitute into the original equation. So my original equation is y double prime minus 3y prime. Is that right? So it's minus 3y prime. That's right. So plus 2y. So that is going to equal x squared plus 1 minus exponential of x. Okay. So now what happened is that I'm going to start substituting. So this is going to be the same as what we have done before. So y double prime, I'm going to have 2c plus exponential of x multiplied by 2f plus fx. So that is going to be my y double prime. So minus 3. So y prime. So my y prime, that is going to be given, let me put a bracket around. So that will be given by 2cx plus d. And then I'm going to have plus exponential x multiplied by f plus fx. Okay, so do not forget about the constant -3 when you multiply later. And then I'm going to have a plus 2. So I'm going to put everything which is in terms of y, which is cx squared plus dx plus e. And then I have plus fx exponential of x. And that is going to equal, so x squared plus 1 minus exponential of x. Okay, so now, so how do you compare is going to be the same as what you have done previously. I'm going to use shortcut. I'm not going to show you in detail, so you should know, like this is already like the 6th example, you should get the idea already. So I'm going to start by comparing the polynomial, so which the highest variable is going to be x to the power of 2. So the term that are related to x squared, there should be only one right here, which is going to be this term right there. So for this case, when I do the comparison, I get that 2c is going to equal 1. So therefore, my c value, that is going to equal a half, 1 over 2. And then I start comparing for x to the power of 1. So let's collect all the term related to x to the power of 1. So which is going to be that. So that is going to be negative 6c. And what else? And here I'm going to have plus 2d. Okay, this is going to be plus 2d, and that is going to equal 0 because I don't have x to the power of 1 on this side. Okay, and because I already know that, Okay, let me solve for this. So we'll get that 2d is going to equal 6c. So that is going to be 6 multiplied by a half. So which is going to equal 3. So I know that my d value, that is going to equal 3 over 2. So that's the d value. And of course, the last one for the polynomial will be the constants, x to the power of 0. So let's collect them. So here I'm going to have 2c. And this is going to be minus 3d. And the last one is going to be plus 2e. And my constant is going to be equal 1 on the right hand side. So now I'm going to find what is going to be the e value. So 2e is going to be 1 minus 2 multiplied by c. So which is going to equal a half. And plus 3 multiplied by 3 over 2. And this is going to be 1 minus 1, so that is going to be 0. So from here, I'll be able to get that e is going to equal 9 over 4. So that is going to be my e value. All right, so now that I already have the value of c, d, and e, so I'm going to proceed with one more, so which is going to be exponential of x. And remember, I did mention this to you before, so that the fact that this is going to be the stage of the calculation. So when you have the case of linearly dependent, whether your calculation is right or wrong for the case of x exponential of x. Okay, what happened is that for x exponential of x, so this is going to be fx, and this is going to be minus 3fx. And so I plus 1, so that is going to be negative 2. And this is plus 2, so automatically it's going to be 0. And I have 0 on this side as well. Okay, so I verified that. So on the left hand side is equal to 0. The right hand side is also equal to 0. So that is correct. So my calculation is correct. And for the case of exponential of x, so now let's start comparing the coefficient. Here I'm going to have 2f. And this is going to be negative 3. So that's negative f. So I'm going to have negative f, isn't it? So I'm going to end up with 2f exponential of x. So minus 3f. So that is going to equal negative of f. Exponential of x is going to equal negative 1 exponential of x. So for this case, what is going to be my f value? So my f value is going to equal 1. All right. So now that I already have all the values, so all I have to do is going to write down the solution. So I can write the solution right away. So the fact that my yc is going to equal a exponential of, what is it before? X. Okay, plus b exponential of 2x. And my yp1, so the first part yp, which is going to be from the polynomial, is going to equal a half x to the power of 2 plus 3 over 2x plus 9 over 4. And when I substitute f, I'll get 1. So it's got to be 1x exponential of x. Okay, so this is going to be my yc. So this is yp from the polynomial. And sorry, this is the sort of yp from the polynomial and until here. And this is my particular integral for the exponential. Okay, so that will be the end of the calculation. So for this one, there is more calculation involved because there are two functions being combined together. And of course, the marks is also going to be more. So compared to the cases of exponential, polynomial, or sine or cosine by itself. Okay, actually, there is one more case, which is the one that we had here. No, not here, not the slide. After linear combination, we also have product of cases. I'm not going to show you an example of product of cases. It's going to be very complicated. But I'm going to show you, I'm going to give you the idea on how do we find the yp when you have product of cases. For example, let's say you have something like this. So this is going to be example. For example, I have y double prime minus 2y prime. Let's make it 3. And minus 2y. And that is going to equal x cos of x. Okay, so what happened over here is that I have a polynomial, so which is multiplied by a cosine function. All right, so from the polynomial, the family of derivative is going to be x and also 1. And from the cos of x, so my family of derivative is going to be cos x and also sine of x. So how do I come out with a yp for this? So as this is multiplication, all you have to do is multiply. So meaning that this multiplied by that, this multiplied by that is going to be one element. So all together we can have 4 elements in here. So first is going to be x multiplied by cos x. So put a constant. So it's going to be cx, so cos of x plus, and then I'm going to have x multiplied by sine. So it's going to be dx sine of x. So this is number 1. sorry, this is, which is x, where's my x here? This is number 1, this is number 2, so this is my third term, this is my fourth term. It doesn't matter as long as you have all of them. And then I'm gonna have E1 multiplied by cos of x, and of course the last one is going to be F1 multiplied by sine of x. Okay, so those are going to be my YP, so you have to put them together. Or if I were to show you another example, so let's say if I have my f of x is given by exponential of x multiplied by x squared, right? So it's going to be pretty much similar. So what happened is that for this one, I'm going to have x squared, x, and also 1. And this one is going to be exponential of x. If I were to multiply, I'm going to end up with 3 terms. So my yp of x, so first term is going to be c, x squared multiplied by exponential x. And then I'm going to have d, x multiplied by exponential x, and the last one is going to be e1 multiplied by exponential of x. So that's going to be the yp. Okay, and then it's going to be the same. All you have to do is find c, d, and e, but because of the terms that you have over here, so your calculation is going to be more complicated compared to like case number 1, 2, 3, and 4. Okay, so you might come across this by when you do the exercise in your book, so that's no problem. You can try to figure them out, and you can try them as well. And I have prepared a bunch of exercises for you to try here as well. So please make sure that you are able to do each of them. Okay, there are combinations of cases that are LI and LD that I want you to experience. Okay, so try them all.